23 is about current electricity. And that's the electricity we think of most of the time that powers the lights and our air conditioners in our homes and businesses. Electric charge will flow anytime there's an electric potential difference. The same way that things fall because of gravitational potential difference. Let's start by looking at a water fountain. Water gives us probably the best analogy to electricity. And if we think about how water flows, it's going to really help us understand how electric charge flows. Suppose I've got a water fountain. Whoops, that marker doesn't work. So here's a water fountain. Make it look like a little basin of some sort. In the park. A little spigot. And it's shooting water out of the top. And all this water falls back into the basin. And we don't have to do anything to make these water droplets fall. These water droplets, when they get shot out, they naturally fall back to the ground because of gravity. Here they have high gravitational potential energy, and when they drop back down, this is full of water. They have low gravitational potential energy. But what is it going to take? We understand why the droplets fall, but why do the droplets shoot out? What's it going to take to keep a continuous flow in this fountain? It's going to take a water pump. The only way this works is if in here someplace there's a water pump. And that water pump provides the pressure that pushes that water back up and out and keeps the charge, or not the charge, keeps the water flowing. The water will stop flowing if we turn off that pump. All the water will just fall back down into the basin and then it will stop. Electricity really works very, very similarly. If you have a piece of wire, I'm drawing it at an angle for no real good reason, and this end was at high electric potential, and this end was at low electric potential, well, charge would naturally flow until this whole thing was neutral. In other words, the charges would redistribute, and as soon as they redistributed, all the electrical flow would stop. We can't get a current unless we have something that provides that pressure, like a water pump. We call it electrical pressure. And for most circuits, the thing that we use, or for the simplest ones anyway, we can use a battery. Here's a picture of a battery. A battery has a positive terminal. Down here it's got a negative terminal. And in the positive terminal of the battery, we literally have positive charges built up in here and negative charges built up down here. There's a chemical reaction inside the battery. That's where this energy comes from, that separates these. Now, if we have a piece of wire, we think of this being high potential. Potential is the same as voltage. And this is being low potential. Just like you can think of high pressure and low pressure. Well, the high pressure is going to cause these. This is a fine point. Positive charge flows naturally from high potential to low potential. So what you can visualize happening is positive charges flowing from high potential back to low potential. And when these positive charges go into the battery, they get pushed, the battery does work on them and pushes them up and right like that. This is called conventional current. Or conventional current is the flow of positive charge. And there's only one problem with this picture. And the problem is, when they started talking about charge, they assumed that positive and negative charge both flowed, and so they started talking about conventional current would be the flow of positive charge. We now know that in metal conductors, only electrons, or only negative charges actually are capable of flowing. The positive charges, or the protons, are trapped inside the nucleus. So what actually happens doesn't look like positive charges flowing clockwise. What actually happens is this. So I can erase that quickly. Instead of having all those cute little positive charges flowing this way, everything I've drawn here is right. The battery separates the charge, but what we now know is it's actually the electrons that are getting pushed out of the bottom that flow. We have these negative charges flowing, these electrons. Now, remember, electricity is a little different than mass. We only have one kind of mass, and it always flows from high gravitational potential to low gravitational potential. But we actually have two types of electric charge. Positive electric charge flows from high voltage to low voltage, but negative electric charge flows from low voltage to high voltage. The flow of positive charge clockwise is mathematically identical to the flow of negative charge counterclockwise. So it's still essentially, for a negative charge, it is flowing so that it will have less potential energy. That sounds a little different. Positive charges naturally flow from high voltage to low voltage. Negative charges naturally flow from low voltage. This is low voltage. They're low, so they will naturally flow around to high. You can think about this as being these negative charges are attracted to this positive charge. Inside the battery, the chemicals do work that keep the negative charges down here and the positive charges up here. So when these negative charges get pushed out of the battery, they're attracted and they go along. Okay. Batteries supply the voltage. Voltage is, quote, electrical pressure. It's the thing that keeps the charge flowing. It doesn't have to be a battery. It can be a power supply. It can be a wall outlet, generator. There's all kinds of things we use that are voltage devices. But the simplest one to draw a picture of course, is just a battery. You want to keep in mind when you're thinking about circuits, current or charge is what flows through a circuit. Okay? We measure current in amps. Okay? 1 amp is a flow of 1 coulomb per second. So you can pick any place in this wire, any cross section. You can pick a point right here. And if I count the amount of coulombs, or the amount of charge in coulomb that flows past that point in any second, that's going to tell me how many amps of current that I have. So we measure current in amperes. We usually just say amps. And an amp means a current, a coulomb per second. If you've got 12 amps, you've got 12 coulombs every second flowing past that point. So charge or current flows through. Voltage is impressed across a circuit. We usually think of voltage being across a circuit. Voltage is what provides that pressure, that keeps that charge flowing. Now, how much current will actually flow depends on something called the resistance. Resistance impedes the flow of current. We generally think of resistance depending on a few things, but let's go back to the idea of water. If you have a water tower, there's a water tower. It's elevated up on a big tower. Usually they paint the high school's name on there or something. If you connect two hoses, if you put a big hose, you're going to get a much larger amount of water flowing out. There's my water. Lots and lots and lots of water through a big hose. If you do a very small hose, you connect it up there, you're only going to be able to get a little bit of water. Okay? This has less resistance. There's more water current. Same thing's true for wires. Generally speaking, if you have two wires and one of them has a cross-section area of A and the other one has a cross-sectional area, now let's make this one have a cross-sectional area of 2A, and the other one has a cross-sectional area that's only equal to A, this one has less resistance. Why? It's easier for current, in this case electrons, to flow through a nice big thick cable than a smaller, thinner one. If you look at power lines outside, they don't use little thin wires like we use in light bulb filaments, or even like we use copper wiring in our homes. They use great big thick cables of wire because they have less resistance. When you make it thinner, you make less. If it's even thinner still, this is going to have very high resistance. It's hard for charge to flow through something that's skinny. It's a difference between trying to drink a milkshake with one of those great big thick jumbo straws and trying to drink a milkshake through a coffee stirrer. There's a lot more resistance when it's thin. The other thing that increases resistance is length. When you have a long wire, it's going to naturally have more resistance than a short piece of wire. So basically, the resistance for a conductor depends on three things. First of all, it depends on the material. Conductors have little resistance. Aluminum, copper, silver, gold, platinum, they're all good conductors. They all have very low resistance. Okay? But they're not necessarily have the same resistance. Other materials, glass, rubber, wood, they have very high resistances. So resistance does depend on the material. If we're talking about conductors, it also depends on the cross-section of the area. In this case, a larger cross-section means less resistance. And it depends on length. A longer wire has more resistance than the same wire that's short. One more thing to think about when we're thinking about resistance is the idea of temperature. Resistance increases with temperature. Okay. A hot piece of wire has more resistance than a cooler one because what's happening when wire heats up, you get what we call thermal energy. The molecules or the atoms in that wire vibrate faster, and because they're bouncing around more, it's harder for the electrons to flow through the wire. Okay? So when you first flip a switch in your house, the wires are cool, the resistance is actually less. But if they've been on longer, the wires will heat up a little bit and increase that resistance. We measure resistance in a unit called an ohm. The symbol for an ohm is an omega. Looks like an upside down horseshoe. It's called an omega. Most conductors follow a law called Ohm's law. For most metal conductors, this is going to work. Ohm's law says that the current is equal to the voltage divided by the resistance. Or the symbol for current is I equals V over R. But that's like any algebraic equation. We can rearrange that and say that V equals I times R. So we see Ohm's law written like this. We also see it written like this. One of my favorite ways to write it is like this. You make a triangle. And you say V, and then you draw a bar, I times R. Now what's so helpful about this trick? If you use it like this, you'll know exactly how to solve. If you're looking for voltage, you cover up voltage, and you know, oh, voltage is current times resistance. If you're looking for resistance, you cover up resistance, and you go, ah, resistance is voltage divided by current. Or if I'm looking for current, I cover up the current. Current is voltage divided by resistance. So when you write it like that, it's real easy to solve problems. So for example, suppose that I tell you that I have something connected to a 12-volt battery and the circuit has 3 ohms of resistance. And I say, well, how much current does it pull? What's the current through this circuit if I connect a 3 ohm resistance circuit to 12 volts? Well, if I'm looking for current, I cover up current and I go, oh, current is voltage over resistance. So 12 volts over 3 ohms, my current is 4 amps. Just that simple. Now, we have been talking about using a battery in our circuit. Batteries generate a certain type of electric current. They make direct current. Direct current looks like this. And I'm going to let this be time. Direct current stays the same all of the time. And the problem we just did, I think we figured out, I can't remember, it was 4 amps or 3 amps? Let's say it was 3 amps. If I have 3 amps of direct current because of a battery, it looks like that. However, direct current, it's easy to get from a battery. It has some problems. It's harder to make or to generate, and it's also harder to transport long distances without losing a lot of energy. We don't want to go into all of that, but if you want to transport electrical energy long distances, alternating current works much better. Way back in the early beginning 1900s or so, there was a major debate between Edison and a man named Westinghouse and Nikola Tesla. Nikola Tesla was a big supporter of alternating current, and Westinghouse backed him. Thomas Edison was a big supporter of direct current, but in the end, alternating current won. We use alternating current in our home. So when you plug something into a wall outlet that's at 120 volts, you're going to actually have alternating current. So what does alternating current look like? If you have 3 amps of alternating current, it really does this. It looks like a wave. Notice in between it equals 0 even. In alternating current, the electrons are not moving in one direction. In direct current, all the electrons are flowing in the same direction. In alternating current, the electrons, they're in this conductor. Here's an electron. They're literally moving back and forth, just like a wave almost. They're just going back and forth. They're vibrating. In fact, the frequency in the US, we use 120 volt, 60 hertz AC, alternating current. 60 hertz means that electron completes 60 cycles every second. It's doing 60 cycles every second. It's changing its direction 120 times per second. So those electrons aren't so much flowing as they are vibrating back and forth. Still does the trick. Still lights up our lights. And these periods where the current is 0 are so brief you don't ever notice the lights going out. Okay? So that's alternating current. See if there's anything else I want to say about direct. I don't think so. I think I've pretty much said it. Now, let's talk a little bit more about current in as much as what's flowing. Electric charge. What kind of electric charge? Electrons. Where do those electrons come from? Do they come from the power plant? When you plug something into your wall outlet, do the electrons flow out of the wall and into? No, they're already in the wire. It's a little bit different than water here. If you go to the hardware store and you buy a hose, the hose is empty. You have to fill it up with water. But if you go to the hardware store and you buy a piece of copper wire, the electrons are already in the copper wire. You're not paying for electrons when you plug into it, when you pay your power bill. You're paying for the energy. You're paying for the work that's done in pushing and pulling those electrons back and forth. Really important to understand that. So how do we even measure this? Well, electric power is given by the formula that power equals the voltage times the current. And we measure it in watts, or often kilowatts. What's a kilowatt? That just means 1,000 watts. Now, if you remember from when we talked about power back in chapter, I believe it was chapter 7, a watt is a joule per second. So if you're using a 1600 watt blow dryer, it's using 1600 joules of energy every second. Okay. If you want electric energy, you have to say electric energy is equal to power times time. Now, if we're working in watts and we want to work in seconds, then my energy, if I'm using power in watts and I use time in seconds, well, I know that a watt means 1 joule each second. I'm going to get energy that's measured in joules. So when I use this formula, if I put in the power in watts and I put in the time in seconds, I get the energy measured in joules. But a joule's a tiny, tiny, tiny little bit of electricity or electrical energy. Power companies actually do it using kilowatts, and they use the time in hours, and the result is a new unit which we know is a kilowatt hour. So when you pay for electricity, when you pay for kilowatt hours, you're paying for electrical energy. You're not paying for power, you're not paying for charge or current or voltage. This is a unit of energy. It's a power times a time. We can work an example. Suppose I tell you that your power company charges 15 cents per kilowatt hour, and you want to know how much does it cost to blow dry your hair if you've got a 1600 watt blow dryer and you run it for 15 minutes. Well, first of all, if we want to get electrical energy in kilowatt hours, we need to change this to kilowatts. 1600 watts is 1.6 kilowatts. Remember, kilo means 1,000. So 1 kilowatt is 1,000 watts. This is 1.6 kilowatts. 15 minutes is 1/4 of an hour. Or 0.25 hours. All right, so the electrical energy used is 1.6 kilowatts, 0.25 hours is going to be 0.4 kilowatt hours. 1.6 times 0.25, that's just a fourth, it's 0.4 kilowatt hours. 15 cents times 0.4 is going to equal I got to get this right. 6 cents. So if you're paying 15 cents per kilowatt hour, your blow dryer uses 1600 watts or 1.6 kilowatts, and you use that blow dryer for 15 minutes, which is 1/4 of an hour, you used 0.4 kilowatt hours of power or 6 cents. 15 cents per kilowatt hour, 6 cents. Okay, let's talk a little bit about circuits now. To have an electric circuit, first of all, you have to have a closed path. In order for the charge to flow, there must be a complete circuit. That circuit's going to have some type of voltage device. That voltage device is going to supply that electrical pressure that keeps those electrical charges flowing. We want to look at two types of circuits that are the most common. One is a series. In a series circuit, there's only one current path. Because there's only one current path, the current is the same everywhere. You're going to answer some questions in Mastering Physics where you're going to use a simulation that'll let you build these circuits, and you can see what happens as you change things. But they look something like this. We've got a battery, and maybe we're going to we can connect in resistors, but I'm going to let our resistors in this case be light bulbs. So if I hook in a little light bulb, and then I hook in another little light bulb, and then I hook in a third one. I'll tell you what, let's not do that. Let's just start with one. We're going to come in and add. Okay, this is a series circuit, but it's really just a simple circuit. There's only one thing in it. If I want to, I could put a little switch that we could open and close. That'd be open so no current flows, and then when I close it, the light bulb lights up. Let's suppose that it lights up very, very brightly, and I'm going to put a lot of, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 little lines to show how bright it's glowing. If I come along and I put in a second resistor, I put in another light bulb, what I'm going to see happen when I add this next light bulb is I just doubled the resistance, because that's like having two resistors instead of one. So instead of having 12 bright little lines to show how bright they're showing, when I double the resistance, the current leaving the battery is going to fall off. Remember, think about Ohm's law. V equals I times R. Well, if this is, say, 12 volts all the time, if I make this number twice as big, I double the amount of resistance in the circuit, that current just fell to half. So instead of putting 12 bright marks, I'm only going to put 6. They're both going to glow, but they're not going to glow as brightly as a single bulb would glow. If I were to put in a third bulb, I've increased this resistance even more. So now that original 12 bright spots is down to 4. So these bulbs are going to be very, very dim compared to the single bulb. Okay? The reason they're going to be very, very dim is because there's going to be much less current flowing. Why? The individual voltage drops, if these are identical and this is 12 volts, there's going to be a 4-volt drop here, a 4-volt drop here, and a 4-volt drop here. That's why they're not measuring as bright. When I only had the one bulb, it got all 12 volts. When I had 2 bulbs, there was a 6 volts here and 6 volts here, so it was much dimmer. By the time I have 3 bulbs, it's 4, 4, and 4. They're having to share that voltage. Okay. So one disadvantage about putting things in series is every time you add something else in series, you increase the total resistance and you decrease the amount of current that's flowing. Because remember, the current that leaves here is the same current that goes through each part. The current's the same everywhere. Another big disadvantage is what happens if one of the elements breaks or gets turned off. If I were to come in here and turn off this light bulb, no current's flowing through this light bulb, that would stop the current for all of them. So when something's in series, if one thing goes out, everything goes out. It's not a very practical way to wire things. So our homes are not wired in series. If they did, every time you turned one more thing on, everything else in the house would get a little dimmer or have less power. And heaven forbid that you turn something off or a light bulb burn out, then everything would go off. Okay? Series circuit's probably the simplest to understand, but it's not that practical. Now, the other type we want to talk about is parallel. In a parallel circuit, there are multiple current paths. Remember, in series, the current was the same throughout the circuit. Well, the current's not going to be the same if we have a parallel circuit. Each branch can have a different amount of current. What is going to be the same is the voltage. In parallel, the voltage is the same in each branch. So here's our battery. And I'm just going to go up here and I'm going to wire in one resistor. Instead of a light bulb, I'm going to use a resistor. Now, resistors are represented by that wiggly line. And I'm going to let this be 12 volts. And I'm going to let this be 6 ohms of resistance. Well, if you can remember, current is voltage divided by resistance. So if this is 12 volts and this is 6 ohms, then I know that I have a 2 amp current flowing. 12 divided by 6 is 2, or 2 times 6 is 12. I have a 2 amp current flowing through that branch. Let's add another branch. Put it right here. Now what you notice is this point is at the same potential as this part, and this is the same voltage. So they both have the same 12 volts. But let's let this be a 3 ohm resistor. Now that's less resistance. Well, if that's a 3 ohm resistor, the current through it's going to be 12 divided by 3. It's going to have 4 amps right here. So notice this time we can have different currents. I've got 2 amps flowing through the 6 ohm resistor, but I've got 4 amps flowing through the 3 ohm resistor. That makes sense. This has less resistance, therefore more current will naturally flow. If I go up here and I add a third branch, here's my third resistor, and this third one I'm going to let it be, I don't know, 12 ohms. Well, how much will flow through 12 ohms? 12 volts, only 1 amp. So I've got 1 amp going through the 12 ohm resistor. I've got 2 amps flowing through the 6 ohm resistor. I got 4 amps flowing through the 3 ohm. But every one of those is a 12 volt difference. They each have 12 volts. Now, every time I added a path, the total current coming out of the battery increased. When I just had the 6 ohm in the middle, all I had leaving the battery was 2 amps. When I added this one, I have 2 amps going through here and 4 amps going through here. Now I have 6 amps. That's less resistance because I have a total of more current flowing. And it doesn't matter. Like if I take that top branch off, you'll see I have a total of 6 amps flowing. No matter how big or small this next resistor is, I know even more current is going to flow. I made it a really big resistor, 12 amps. But notice now we still get 1 more amp of current. So the way this works is I've got 7 amps total. If I do a total, leaving the battery, and I have 7 amps total going back into the battery. 7 amps leave, 7 amps go in. But when they reach this junction, they split up. 4 amps goes through here, 2 amps through here, 1 amp through here. Every time I add another path, more current has to leave the battery. In fact, one of the reasons that we have circuit breakers and fuses in our house is when we're wired in parallel. If we turn on too many things, this current can get too high. Suppose I change this to 1 ohm. If I have 1 ohm here, that will draw 12 amps of current because 12 volts divided by 1. Well, now I'm going to have a total of 4 plus 6 plus 1. I've got 18 amps. If I had a fuse in here, I have a 15 amp fuse. What's it going to do? Anytime the current gets greater than 15 amps, it's going to break this circuit. Basically, fuses melt. There'll be a break in the circuit. That's because 18 amps could be dangerous for that circuit. You want to avoid too high of current because too much current can cause the wiring to overheat and catch your house on fire. So, if you've ever gone, we don't really use fuses so much in our homes. Now we use circuit breakers. Circuit breakers are more like a switch. And that switch will pop open. If it's a 15 amp circuit breaker, it's going to pop open anytime the current goes over 15 amps. So when you turned on this thing that drew 12 more amps of current, it's going to pop open to try to keep your home safe. See what I haven't said. I think that's about everything. Good luck. If you have questions, shoot me an email. Trouble with your homework, shoot me an email. I'll be seeing you.